The math required to solve problems in this video series is primarily calculus, but only some differential equations will be solved. The more complicated flows resulting from more complicated geometries will not be presented in this video series. Okay. In this first chapter, the basic information needed in our study will be presented. Enjoy! To be more specific, in this first section, basic fluid properties like density, pressure, specific volume, and weight are going to be explained.
To distinguish between units and dimensions and introduce some pretty basic fluid properties. So first, looking at units, you should have seen this in your previous studies. So units are things like kilograms, newtons, meters, seconds, among other things. Dimensions construct units. So the dimensions of kilograms is m, dimensions of, say, meters is L, and the dimensions of seconds is T. And we can construct things like newtons out of these three dimensions. And this forms the MLT system. The MLT system has four dimensions, M, L, T, and theta, where theta is temperature. You won't use temperature too much in fluid mechanics, but it's still part of the system. You may see in some of your textbooks the FLT system in topics on dimensional analysis. That's just the system they use in places like America. So it's the same thing, they just use force instead of mass. So we're going to go and construct the second law of motion, F equals ma, using dimensions, the MLT system. So we know the units of each of these variables. So F is, the units for F is newtons, for mass is kilograms, and for acceleration it's meters per second squared. So to find the dimensions of this, we write F between two square brackets to inform that we're finding the dimensions of force. The dimensions of kilograms is mass, dimensions of m, meters, is length, and of seconds is time to the minus 2. So the answer would be ml on t squared. And we'll see more on that in the topic on dimensional analysis. So now on to density. This is a pretty important fluid property. You'll be using it a lot. It's given the symbol rho, which is a funny P. That equals mass on volume. So that has units kilograms on meters cubed. So the dimensions of rho equals mass from there, and m is length, so L cubed. So we'll be seeing a lot of that.
As temperature increases, the density, so as temperature increases, then the volume would increase, because as you get hotter, volume starts to increase of liquids. Now this is true for most liquids except for water. It's not so much true for water, because water at 4 degrees has the highest density, and as it becomes cooler, as it becomes 3, 2, 1, 0, the density starts to decrease. And that's sort of why I guess ice floats in the Antarctica. So anyways, where were we? Yes, so if the kilograms are the same and we increase the temperature, what happens to volume? Well, volume increases. So if volume increases, what happens to density? So if volume, oops, let's just see here. Okay, so if volume increases, what happens to density? Well, therefore, so what happens to density? Sorry about that. So what happens to density? Well, then the density, if the volume increases, then the density would decrease. So the density would go down. And that's sort of true with most liquids. Like I said, when they become hotter, their density usually decreases. Second thing we're going to talk about here is specific weight, and that is also called gamma. So it sort of looks something like this. Gamma is equal to the weight over volume, and the weight is equal to the mass times gravity. So therefore you can say mass times gravity over volume. Now remember, mass times gravity is what? Mass times gravity is density. So therefore we can say density times gravity. So the gamma is equal to density times gravity.
You may have learned in your chemistry class that the standard atmospheric pressure is 1 atmosphere, which is about 101,300 pascals or 101.3 kilopascals. In AP Physics B, we round this number to 10 to the 5th pascals, and it can be convenient for you to memorize it. You probably also know that 1 atmosphere is 760 millimeter mercury or 76 centimeter mercury. Since pascals is really newtons per meter squared, this means normal atmospheric pressure provides 10 to the 5th newtons, 100,000 newtons of force per meter square of area. The area of my hand is about 0.013 meters squared. Pressure, by definition, is force divided by area. So the force equals to pressure times the area. The pressure, the standard atmospheric pressure is 10 to the 5th pascals. The area of my hand is 0.013 meters squared. So this gives us 1,300 newtons. There are absolute pressure and gauge pressure. The absolute pressure is the real pressure. So if it says pressure, it means absolute pressure. Gauge pressure is the absolute pressure minus the atmospheric pressure. We usually use P sub O, PO, for atmospheric pressure. So gauge pressure is like the extra pressure above the atmospheric pressure. For example, if we inflate a tire to a gauge pressure of 250 kilopascals, it means the pressure inside the tire is 250 kilopascal more than the atmospheric pressure. If the atmospheric pressure is the standard value of 10 to the 5th pascals, then the absolute pressure inside the tires would be the gauge pressure plus the atmospheric pressure. See, the absolute pressure is the gauge pressure plus the atmospheric pressure. So this would equal to, the gauge pressure is 250,000 pascals plus the atmospheric pressure. If a problem doesn't say anything, that means we will use the standard atmospheric pressure for the atmospheric pressure. So it's 10 to the 5th pascals. We add these two together, we get 350,000 pascals. And that's the absolute pressure inside the tire. We may use gauge pressure instead of absolute pressure because sometimes what's important is the amount of extra pressure above the atmospheric pressure, as in the case of tire pressure.
Okay, now let's start basic differential equations in fluid mechanics. Now we have learned basic fluid properties such as density, pressure, specific volume, and weight. And we have also learned about basic differential equations used in fluid mechanics. See you in the next lesson.